So very good afternoon to you all. So welcome to the session. Today in today's session we will discuss about some basic programming concepts. So specifically we will be discussing about the concepts related to geocomputation. And the programming language which we will be discuss about is the Python. So this will be our overall presentation outline. So the first I will discuss about Python. So here I am assuming that the viewers are comfortable or they have at least some basic idea about some of any of the programming language, not maybe very specific to Python, but I assume that you are already comfortable using some of the other programming language. You are comfortable using any of the programming language, may not be specific to Python. So I will introduce you to the Python. Then we will discuss about like why Python and why Python has become so popular. Then we will discuss, show a small program using write a small program, and I will introduce you the different basic programming concepts. Like if you have done programming, if you have already done programming, either using any of the programming language, maybe C, C++, or Java, then you can pick up these things quite easily and very fast. Then we will discuss about some basic elementary raster data processing. How do we do the basic raster data processing using Python? So Python, as all of us, Python means Python is one of the most popular programming languages. So Python is one of the most widely used, interpreted. So Python is an interpreted programming language, interpreted, interactive, and object-oriented programming language. Actually, Python is very popular because of its multiple features. Actually, it is widely used. It is basically an interpreted programming language. So once you write a program, the program does not get translated into the machine code directly. I mean, there is no compilation step. Directly the interpreter takes the statements step one by one, and directly the statements get executed. Plus Python, actually there are basically two programming paradigms, if you know about. Then one is object oriented and another is functional programming. So Python supports both of the programming paradigms. So the name of the Python, like the name Python initially appears quite weird. Like Python means people assume that a big snake. So but name of the Python programming language comes from an old BBC television comedy series. I think the name was of the series was Monty Python's Flying Circus. So I think the creator, or the original creator who started Python, he was a fan of this particular comedy series. So I think based on this only he has given the name of the programming language to be the Python. And this is like one of the most amazing features of the Python is that generally what happens, creating a programming language is a very big project. So generally a single person cannot develop a big a programming language. So if you see any of the programming language before, so it was all of the programming languages was a teamwork. A lot of people had contributed to development of that particular programming language. But in case of Python, so the basic interpreter of Python was written by a single person. So the name of the person is Guido van Rossum. So he was a Dutch person, but it doesn't, if we say that it was just a work of a single person, we don't say that whatever feature we are seeing today in the Python was, or everything was developed by the by the same person. It is not so. Actually the Python has evolved over the time. So actually he just created the basic Python but now a lot of user communities around the world are contributing to the development of the Python, and they are adding daily new and new features to the Python. And actually you must be seeing that Python is continually updating. New and new versions of the Python are coming, I think maybe quarterly. So these were the goals, like when the Python was created, because before that Python also there were a lot of programming languages in use. So the first goal of the Python was to create an easy and intuitive language. So other programming languages at the time when Python interpreter was written was not so easy and intuitive. Right. So the first goal of the Python was to make a language that is the language must be easy and intuitive, but it must be as powerful, it must be comparable in terms of power to the programming languages which were existing at that time. Then it needs to be open source so that anyone can contribute to its development. The code must be understandable as plain English. It must be suitable for every task, because the programming languages which were developed before were for some specific need. Like some programming languages were specifically for embedded system, some programming languages specifically for web development, but Python was supposed to be a general programming language so that it can be used for any kind of task. So almost like after seeing over 20, after seeing the results after 20 years, now we can see the seeing the proliferation of Python. Now we can say that the goals which were set by the creator of Python while developing the Python, almost all of these goals have been met. And even now some sources say that Python is the most popular programming language. It has surpassed even Java. So now it is the most, so most of the programmers in the world are now using Python for their work. So like now the question comes, if there are so many programming languages for there are so many programming languages to choose from, then why should we go for the Python? So I think this is the one of the most compelling reason for going for Python. Is it is the easiest to learn. So once, even if you are not, so suppose if you are if you have done programming in any other programming language, then it's quite easy for you. But even if you are very new to the programming, so the new users also can learn Python quite easily, and it is easy to teach as well, because instead of focusing on the nitty gritty of the programming language or learning tricks, so we need not, because the syntax of the Python is quite simple, so it's easy to learn. And so while even for teaching also, we need not teach you the different tricks of the programming language, so it's quite easy to teach as well. Then because it is easy to learn and teach, so definitely it is easy to use, understand, easy to obtain, install and deploy, because being an open source software, you can quite easily get it on the internet. There are multiple sources available from where you can download, then you can install it and deploy it. Then plus it is platform independent. Platform independent means once you write a program in Python, maybe you are writing in Windows operating system, the same program you can port it to Linux or Mac operating system. But in case of other programming languages which were not platform independent, like the syntax, sometimes slightly the compiler anyway changes from platform to platform, but even syntax also was changing from the platform to platform. But in case of Python, once you write a program, so the same program can run in any of the operating system. Plus it supports both object oriented as well as function oriented programming paradigms. Plus, as I said, that it has a great community support. Actually, there are a lot of communities worldwide which are contributing to development of the Python. If you are stuck somewhere, then you can take the help from the community, and there is a very good documentation also is available, and continuously every day new and new features, new and new libraries are coming and getting added to the Python. Plus it has a rich ecosystem, like there are a lot more other libraries or tools are built on the top of Python. Like there are tools for visualization, there are tools for deep learning, machine learning. So these all you can incorporate to your project quite easily, because they all are using the same Python library. So then if you see Python, where we can see Python in action. So Python is almost everywhere, whether you take web development, GUI, scientific and numeric computation, different software development applications for government or non-government applications, system administration. So any task you take, as you say that this was the initial goal of the Python, goal set for the development of Python, that it must be usable for every kind of development. So any field of web software development you see, everywhere Python is there. Plus it is used extensively to implement complex internet services, like so many of the search engines, cloud storage tools and social media platforms like Instagram, Facebook also, they are also using Python in some or other way. And plus, because Python is evolving daily, so more and more everyday use applications are being written in Python, because there are a lot of communities which are contributing to development. So they are writing new and new application to the Python. Then among geospatial community also, Python is quite popular. So basically actually there are two versions of Python. One is Python 2 and another is Python 3, and both of these versions are not compatible to each other. So like there are some legacy software which just run on Python 2 only, because then, but it is suggested that when you are starting a new project, you must start with Python 3 only, because that offers a lot more functionality and features compared to Python 2. Then actually Python implements, there are multiple sources from where Python is available. Like suppose if you have worked on C, there were different compilers for Python like Turbo C compiler or NCC compiler. So there were different compilers. Similar way, Python also is available from multiple sources. So the traditional or basic whatever Rosam created, that traditional is called the C Python. So the interpreter of the Python was written in C programming language. So this is called C Python. So whatever Python you are getting from the python.org portal, so that is C Python. Then there are other implementation like Jython is another implementation of Python written in Java programming language. So the interpreter of Python which is written in Java programming language is called Jython, but it doesn't offer all the features which C Python offers, but Java programs you can call directly in this as well. Then there is another distribution called MicroPython. Then one of the most popular distribution among data science community is Anaconda Python. Actually, Anaconda is quite popular. It is a big package manager, environment manager, and a distribution of Python as well. So Anaconda Python is also quite popular among people. So these are the different terminologies actually we will be referring. Like one is called something called module, packages, and libraries. Actually, module, packages, and libraries save you time. Actually, these are the piece of codes and piece of codes written, some very useful functions or piece of codes written by some other users and nicely packaged in modules and packages so that we can reuse them. Like suppose if you are if you are going to start writing programs for solving some specific problem, then we need not reinvent the wheel. Actually, most of the things will be available in the forms of these libraries and packages or modules. Then we can just reuse them directly. So these help us. These reduce the time. These save us time. Actually, they reduce our development time. So we will be actually what happens by default. All these modules and packages doesn't come to the Python interpreter when you start the Python interpreter, because you may not require all these things. So these modules will be available, but suppose if you need some specific module, like suppose if you want in Python interpreter by default math functionality doesn't come. So suppose if you want to import these things, and then you need to import these modules or libraries to your Python interpreter, then you can start using it. Then for for the demonstration, we will be using something called Jupyter Notebook. So Jupyter Notebook is the original web application for creating and sharing computational documents. Like all your live code you can write as you are writing in your notebook. So it is a web based, like all your Python code you can write on a web browser, but on the back end there will be a Python kernel running, so it will be interacting with that Python kernel, but you will be writing the code in the web browser, and the your command will be sent to the Python kernel for execution. Python kernel will execute it and return the result, and the results in a nice formatted text can be shown to you on the Jupyter Notebook. So Jupyter Notebook supports over 40 programming languages including Python, R, Julia, and Scala. So you can produce code plus as well as rich and interactive output, maybe like HTML, text, images, video, latex, or anything. So and big data tools, Apache Spark, and all also you can. So anyway, this is not important. Then actually, suppose if you want to use Python, then first thing is you need to install everything on your system. So that is sometimes it may be a cumbersome task. So suppose if you don't want to install everything on your system, so there are many cloud service provider which are providing us free cloud-based services for Python. Like suppose if you have an Google account, then directly you can use Google Colab. So Google Colab also is Colab or Collaboratory allows us to write and execute Python in our browser with zero configuration required. Actually, it's a ready-made thing for you. You need to just log in with your Google credentials, and everything is set up for you. Python is installed. They give you a virtual machine in which Python is already installed. So all basic libraries which are required generally for geospatial data processing or machine learning are come pre-installed in this. You need not take pain of installing all the system. So like zero configuration is required. You can just log into the Google Colab and start directly using. Plus, suppose if you are working on deep learning and you need access to GPUs, so they give access to GPUs also. And once you have created a notebook or thing, something like that, then you can share quite easily with your friends. Suppose you can access, suppose if you have some data you have stored in your Google Drive, so that also can be accessed using Google Colab. So then there are other options, like you can go to Anaconda Cloud as well. So with this basic introduction to the Python, let's jump to the practical. Now I will be, because I will not be installing Python on my local system. We will be just going to the Google Colab, and there we will see how do we write Python programs on the Google Colab. So for this to get started, you just need a Google account. That's all. So on the Google, I will just type Google Colab, and it says this, and here we need to sign in with our credentials. I think this is some other user. So once you log into this, you will see so Google Colab is let's say that this is an interactive environment for writing codes in a web browser. So basically, as I said, that in Google Colab you can insert text or you can write executable Python code as well. So basically, so whatever you are seeing here, this everything is called a cell here. A cell, there are two types of cell in Google Colab. One is called the code cell and another is called the text cell. Code cell means in the code cell you will be writing the executable Python code, and in the text cell you can insert images, write formatted text, or you can write latex equation and so on. So suppose here, like you can see this block of the code, this is an executable Python code, and these all are text. So in the text you can see that this is the formatted text, like this is, if you see, this is an image, so this is an HTML text, and this is the formatted output of this HTML text, and this is, you can insert with links to the videos and so on. Then you can go through this. Once this is done, then first thing what you need to do, you need to create a new notebook. So there are multiple things, like once you are, this is like you can disconnect, connect, restart your kernel and so on. So first thing you need to do, you need to, actually I have already written a notebook here and I have stored in this Google Colab. So first I am opening the notebook. So you can just open notebook and I'll say this lecture 1 wgcapd lec _3. In this file I have written my code, which I will be using for demonstration. So as I said that there are basically two types of cells. So one is code cell and another is text cell. So in the code cell you write executable Python code, and in the text cell you need to write any formatted text. So let's first discuss about basic Python constructs. So like once this is done, then you can click here on the connect. So it connects to the Google Cloud. So once it turns green, it means the system is ready. So the first customary thing what you do in a programming language once you're starting is, so like something, if you want to print something on the console, like if you execute some software, so the software will be prompting for user to enter something, or it may displaying some message to the user. So suppose if we want to display some message on the console, so in the Python, so the basic thing for printing something on the console is called print, like print, and inside the parenthesis you can print like hello world. So this particular command displays the message hello world on the console. Now suppose if you have to execute this particular statement, you can just click either on this or you can just run. So actually here I am assuming that you already know some of the some programming language. You understand the concept of what is console, what is the printing message on the console, what are the variables and all. So like print hello world. So here you can see that print, you can assume it like a function, like this is similar to something like a mathematical, or as of now you can assume that print is something a black box in which you put some value and it gives you back some result. Like print, we are putting this hello world to this and it is returning, this is printing this hello world on the console. So the second most important thing in the program is something called value. So value may be like number of students in a class, or it may be like name of a person and so on. So the values can be like integer, string, or it can be a floating point number. Then once we attach a name to that value, that is called a variable. So in other programming languages, for defining a variable, you need to define, like first you need to define the data type of that variable, like whether it will be holding an integer value, a floating point value, or maybe a string. But in case of Python, a variable can be defined just like you need to give the name of the variable, like I say var underscore 1. Then suppose if you want to assign some value to that variable, var1 equal to 10. So I am assigning a integer 10 value to the name var1. Now suppose if I want to print the value of this particular variable, I can just say print score 1. I say print var1, this is the end. Now suppose similar way, now suppose if I want to write a program for calculating, you assume a difference between, write a program for calculating the difference between two numbers, right? So there all mathematical operations are available here. So here I will be writing like number underscore 1. So in the number 1, and I have stored the value in there, assume 20.0. I have stored value floating point value. And similar way, suppose if I have to, I will now define a second variable called number underscore 2, and in that I've stored the value of 30. And suppose I want to calculate the difference between these two numbers. So I will call it diff new variable number underscore 2 minus then I say print diff. So this is like defining a variable like difference. So then you change. So this is the basic syntax. Then similar way for defining a function. So suppose if you want to write a new function, so the new function name starts with the keyword def. Then you need to give the name of your function, like if you want to say my function, and parenthesis. Suppose if it is taking any argument, you can specify the name of arguments. And actually the blocks of code in Python are delimited using the indentation. In other programming languages, we use curly braces, but in case of Python, these are indented. Like the lines which are at the same indentation level make a block of code. Like here I will be writing print welcome to my function. Now this is, we have defined a function. Actually once definition of function doesn't make anything. Now we need to call the function. Suppose if you want to put it into action, then I will call my underscore function. Sorry, it has my. Now you can see welcome to the function, it has printed. So this way we can define functions. So with this basic familiarity with the basic syntax of the function, now let's go to the main topic of our discussion today is the how do we do some elementary raster data processing using Python. Actually our basic idea was using Python for geocomputation. So geocomputation means doing some processing on some kind of geospatial data, maybe raster or vector. So doing some processing, basic processing on any geospatial data and extracting some useful information from that geospatial data. So let's now in today's demonstration we will see how do we read a TIFF file or a GeoTIFF file. Then we will see how do we visualize that TIFF file and do some processing on that image. And then later on we will see how do we visualize a multi-band, single band or multi-band raster. Then we will discuss, suppose if you want to calculate NDVI from two images, we will discuss about that and see how it is done in Python. So actually if you know about this scripting, then suppose if you have to do a lot of data processing, like you have uh, a huge amount of data to be processed. So instead of manually processing those data using some software, so what you can do, you can write the scripts in Python and automatically you can actually automate many of your manual tasks using Python. So anyway, I think in your previous lectures, this basic of this was covered. Anyway, for the sake of completion, I will be covering these like raster data. So what is raster? Raster data represents objects or variables on the earth, on or near the earth's surface, using a matrix of values, right, in the form of pixel cells or grids. So a raster can have multiple layers. So every layer can represent like the same information at different temporal intervals, or it can represent the reflectance values in different electromagnetic wavelengths. So like suppose if you are seeing a raster image, the image looks like this, and ultimately the image will be made of the cells or a grid of cells. So every cell will be representing some information. So this cells value may be representing some temperature at some particular point of time at some point on the Earth's surface, or it may be representing some electromagnetic EM reflectance in some particular band, maybe red, green, or blue. So like ultimately the image will be represented as a cell of grid of cells or numbers. Like here every pixel is representing some grayscale level. So the image can be visualized as a grayscale level. It may be temperature or reflectance. It can be. So an raster image can be a single band image. The single band image can be represented maybe either a binary image containing 0 and 1s, or a grayscale image, or it can be represented using a color map. And raster image can be multi-band image as well. It can contain multiple bands. By combining these bands in RGB and RG and B combinations, we can create a composite from that, or composite image. So that may be a false color composite, or it may be true color composite as well. So this way, by combining R, G and B different bands, we create a colored image. So like this is an list 3 image of the Haridwar area. You can see that this is a natural color image of Haridwar area, and this is the image of Chenab bridge on Chenab bridge acquired by Cartosat 2 series spacecraft of ISRO on 12/6/2022 of so now let's see how do we do. So for reading and writing, as I explained, that there will be certain libraries. So the library which we'll be using for reading and writing the raster data is called GDAL. So GDAL stands for Geospatial Data Abstraction Library. It is an library for reading and writing raster as well as vector data. So GDAL represents a single, actually it supports multiple vector as well as raster data sets. So irrespective of the underlying format, maybe it may be a GOT for IMG or format, whatever format. So GDAL driver will be representing the image as something called data set. So in the data set, we will be doing the operation. So what are the advantages of using GDAL? GDAL is free and open source. It supports over 80 plus image formats and map projections. So almost all the raster as well as vector formats which are available, so almost all are supported by GDAL. Plus it offers command line as well as C, C++, Python, R and Java APIs also. Like if you are not comfortable using a programming language, but still you want to automate many of your tasks, so then Python offers you the command line utilities as well. So GDAL functionalities you can call using command line utilities as well. There you need not write a Python or Java program. Directly you can write some basic like we are writing in Windows commands. So similarly you can write commands using Jidal as well, and then you can save them in a batch file or script file, then this can be run automatically. Plus it is used extensively by the world's large geospatial data services providers. It has extensive test suite and active developer community. Jidal also supports for vector data sets also. So as we explained that irrespective of the underlying data format, so GDAL represents any image what it can read as a data set. So once you read an image using GDAL, it will be represented as a data set. So the data set in turns will have multiple bands depending on your image, how many bands are there in your image. It may have one or two bands, plus it will have the geo transformation and projection information, like the information with the help of this information how the image needs to be projected on a map. So geo transform and projection information will be attached to that data set, and a band in turn will have actual data array. As we said that an image is just a matrix of values, right? So the band in turn will have the matrix values, and it will have some overview bands or what they call reduced resolution data sets. So the same image covering the same extent but at the coarser resolution, so that when you are looking out at the bigger area, the rendering on the screen becomes faster. Then this is about map projection, must have been already discussed. We need not discuss about this. So now this comes the main part of our code. So as we said that we will be using GDAL. So there is a package or library called OSGeo. So the name of the package is like, suppose if you want to import some additional functionality into your Python code, by default all the functionality which are available in Python doesn't come to the Python interpreter. Like suppose math functionality by default is not available to the Python interpreter, and suppose if you want to import that math functionality, so for that you need to execute this import and math. So if you write import math, so entire math library gets imported to your Python interpreter, and now you can use the functions available inside this Python math library in your program, like math dot something. Suppose if I want to calculate like these are the functions available inside the math library: math, kinds, isnan, hypot, gcd, gamma. So these are all functions available: exponential, power. So if you want to calculate power, so then like this you can call 2 raised to the power 3, calculate 8. So like this. So similar way, there is a library called OSGeo. Like from the OSGeo, we are just import. OSGeo actually contains many more things, like for vector data processing there is a module called OGR, and for vector data raster data processing it is GDAL. So from the OSGeo package we are importing the GDAL module. Like from OSGeo library we are importing GDAL, and we will be using another library called matplotlib that will be used for visualization, and NumPy will be handling for matrices, because as we said that image will be represented as a matrix. So first thing, because what happened here, I have stored all of my data whatever I will be using here in my Google Drive. So before using this accessing those files, first we need to mount the Google Drive to our Google Colab. So for mounting a Google Drive, you need to just click on this folders icon, and on the top there is mount drive. This icon is there. If you click on the mount drive, it inserts a piece of code to your Jupyter notebook. Right now, for linking your or mounting your Google Drive, you need to run this piece of code, like from google.colab import drive and drive.mount. If I run this, it asks further, then I need to provide access to Google Drive to Google and allow. So this my Google Drive is mounted to my Google virtual machine, whatever Google has given to me. And now if I see it, now if I refresh here, now see actually here you can see that drive folder is shown here. Inside drive, my drive, and inside that I have a folder called PRSD bio. In that I have stored the data like all images. So we will be visualizing these images. we'll be using these images for our demonstration. So like first thing is we need to import all the required functionality into the Python interpreter, like Python shift run. And first what I am doing, I am changing my working directory to be the directory where the data is available. Like OS is a library for operating system related functions, then os.chdr, with I am changing my working directory to be the directory where my data is available. So inside this I have a file named chennai.tif. So this is an image of Chennai area. The image is acquired by resource@2 LISTRI sensor of resource@2 spacecraft of ISRO. So this is I think this particular image has 4 bands. So the bands are, band 1 is green, red, near infrared, and SWIR bands are available in this particular image. Now let's see how do we read the file. So I have created a variable called file_name, in which I have stored the name of the file which I want to read. And for opening the file, we need to call the function called gdal.open. gdal.open, and pass it the name of file which we want to read. So I'll write here gs equal to gdal.open. File name dsify, right? Now as I explained in my previous slide, that once you read a file using GDAL, the entire image is being represented as a data set. Now here you can see that dsify.ds variable, it is a data set. Now suppose if you want to see, like in the ds there are different functions available. Like if you want to see what file we have read, this particular GDAL driver, which file it has read, so if you call ds.file list, it says chennai.tif and chennai.tif.aux.xml. Now suppose if you want to query like how many pixels are there in your image, what is width and height of your image in terms of pixel, so then you can call this function ds.rasterXsize. It gives you the dimensions of pixel in width x direction, and similar way you can query raster.ysize. So the image is 1151 1 by 1. So in the image there are 1151 by 1151 pixels in our image. And suppose if you want to query the coordinate system, like what is the coordinate system of your image, so then you can call the function ds.getProjection. So it says that the image is stored in geographic coordinate system. Right, you must have studied in your previous lecture about the coordinate system and projection system. So this particular image is stored in geographic coordinate system. Then you can get the geo-transform information, like affine transformation information attached to the image. So with the help of these affine transformation, we can map we can convert from the image coordinate system to the real world coordinate systems. And then you can calculate with this the coordinates of the corner and so on. Okay, now similar way, now suppose if there is some metadata attached to the image, if you want to fetch the metadata from your image, then you can call the function ds.getMetadata. So it has just a single metadata. This is showing like area or point. This is an area. So the pixel represents an area, not an point. So like suppose if you want to query how many bands are there in your image, so ds.rasterCount, if you do, it says that there are 4 bands in this particular image. So suppose if you want to iterate, like because there are 4 bands in this image and you want to iterate over all these bands one by one, suppose if you want to calculate the statistics, so that also you can done like iterate like this. It says, and now this is again the same thing. Now suppose this is actually for loop is something like the syntax of the for loop in Python is a bit different from other programming language. Actually, so like here, as we explained that a data set in turn will have bands, right? Now suppose if we want to iterate over all bands of our image. So first we are opening the data set for data set reading, then we are iterating over the all bands. Like from suppose if you want to fetch some particular band from your data set, as we said that the data set contains bands. So like you can call this function on your data set dot get raster band. So data set dot get raster band, then you pass it the argument like which particular band you want to fetch. Get raster band 1, it fetches the band 1. Like here, if I write here band, so it fetches the band 1 from that image. Now suppose if, as I said, then now the band will contain the matrix or cell of values. Now suppose if you want to see the cell of values, values of these all the cells, so then on the band I need to call the function band dot read as array. So let us see how does that data look like. So the data, so like now here you can see that these all intermediate values are hidden because of the performance reason. So here you can see that pixel 1 has the intensity 126, pixel 2 has 132, and this way there are totally 1151 by 1151 pixels. Similar way, now suppose if you want to iterate over all the bands, like get raster band fetches a single band. Now because in our image there are 4 bands, now suppose if you want to iterate over all of these bands, then we can loop it over using a for loop, like for I in range 1 to how many bands are in our image, then we will be calling band ds dot get raster band, and every band there is a function called compute statistics. So it calculates the statistics about that band, like min, max, standard deviation. So with this we get the basic statistics of each of the band in our image. Okay, now let us see how do we visualize the image, because this we have read the data. Now suppose if we want to visualize our image, then for that we have used the function matplotlib, and the function used for visualizing the image, actually the contrast of the image is not so good, so it is not visible clearly. Like I will change the color map, or I say try to read the different band, so it may look slightly better. So now at least now you can see that the image looks like, so this is a band 4 of our, this is a black band because we have just fetched the single band and we are displaying it as a grayscale image. So here you can see the image, and similarly suppose if you want to visualize all 4 bands, you can create multiple, so you can visualize all 4 bands also together in matplotlib. Now this is a single band image. Now suppose if you want to visualize a multi-band image, like if you have, our image has 3 or 4 bands, and out of 3 and 4 bands we want to create some standard false color composite from our image. So let us see how do we create a false color composite, because the demonstration here we are using this particular image Chennai.tif has 4 bands. So the bands are green, red, NIR and SWIR, and then we can select any of these combinations to be represented as RGB. So for that we need to call, like here by default band.read as array was reading a single band from our image. Now suppose if you want to read multiple bands from your image, then you can call like ds.read as array. So instead of passing it a single argument, you can pass a list, like I want to read band 3, band 2 and band 1. Band 3 to be represented as red, 2 as green, and 1 I want to represent it as blue. So NIR is going to red is going to green, and green is going to blue. So multi-data, then we need to actually reformat the data for this thing, and same function plt.imshow, and pass it the array which contains the data. Here now you can see the image. So this is a false color, standard false color composite for the same image where we visualize the single band. Here we have combined 3 bands together and seeing it as a single image. So similar way you can create other false color composites from that, like band by combining band 4, band 3 and band 1. So then now the same image will look a bit different. So depending on the which feature you want to highlight, you can select the particular band combination for creating that false color composite. Now you can see that the same image looks a bit different. Similar way you can create other combinations. It's like this, you can create other combinations. Then suppose if you want to create a mosaic. Mosaic means when there are images covering different spatial extents and you want to combine them all together to make a single composite. Right, so here I have in my folder I have these 4 images, and suppose let's visualize these images. How does the look? So like these are 4 images, and suppose if you want to combine them together into a single image. So for that there is a function available in GDAL called GDAL.warp. So GDAL.warp, you need to pass it like then your destination, like in which file you want to save your output, and second argument list of files, like which all files you want to combine together into a single file. And there are many more arguments, like these 2 arguments actually are the required argument only, other are the optional arguments. So like if I do like this, so then it creates a new file with name mosaic_images.tip, and by combining all these 4 images together. Now if I run this, you can see that these all 4 images got combined into a single image. Actually this is looking different because this is a different band. So just for sake of showing only I have issued it here, because this pixel intensities are in this is in a band 5. So because of that the intensities level and in this are different. So this particular patch is looking a bit different from all those. So this way you can see that by using GDAL.warp we can create a mosaic of images. Then there is something like, suppose if you want to calculate NDVI for your images. Let us see how do we create NDVI from the image. Actually the data is same only, so this is same. So in this I have stored the images like NDVI is the formula for NDVI is NIR, like pixel intensities, like for every, and this is used for identifying the vegetation pixels. So and NIR minus red divided by NIR plus red. So the green image, my pixel intensities in green band are available in this particular file. So the name of file I have stored in a variable called green image. So the red band image I have stored in the variable called red image, NIR in NIR, and SWIR in SWIR image. And so now I will be running. So now first I am reading the red image, then NIR image, then fetching the data from that. Now red underscore band. So I think it could not find the file. I have not unzipped. So from the image, now suppose if you want to calculate NDVI, so we need to just write the formula like NDVI equal to NIR minus red divided by NIR plus red. And now if I see this particular image, now you can see that from our original image, pixels which contain vegetation are shown in the white color or bright, and pixels which are non-vegetation pixels are shown in darker color or black color. So similar way, suppose if you want to calculate NDWI is used for identifying water pixels in your image. So you can call like green. So the formula for the NDWI is NDWI equal to green minus NIR divided by green plus NIR. So same thing, we are reading the files. So green minus NIR divided by green plus NIR, we apply the formula. And suppose if you want to visualize like, so now here what will happen? All the water pixels will be shown in the white color. Now you can see that. So this way you can easily use Python for doing any kind of analysis which will be done on every pixel. So here you can see that it has highlighted like all the water pixels are shown in white color, right? Now suppose in your image what you want to do, you want to mask all non-water pixels. That also can be masked using just a single command. Like you can run the command np.where ndvi is less than certain threshold. Like you can choose the threshold. Like if I see the image here, so it says like above less than 0.1. So all the pixels which are less than 0.1, I will just replace them with 1 and others with 0. So this way now you can see that all the water pixels, so there may be some false positive as well, but you can see that by this we could extract all the water bodies from our satellite image. Like all the pixels which are water pixels only have come up and all other pixels have been masked. Similar way, there are other indexes, like suppose if you want to calculate the NDBI or normalized difference built up index. With that you can identify the areas which have some built up. So the same thing, the formula for NDBI is sphere minus NIR divided by sphere plus NIR. We read the same files there and apply the formula and visualize the images. So this way you can identify the areas which have built up. Right, so with this we come to the end of this lecture. So we discussed about basic of Python, like what is Python programming language and why it is so popular. Then we discussed some basic syntax of the Python. Then we discussed about raster data processing using Python. So the basic library which I introduce you is JDAL. Actually, it is very difficult to cover all the features of JDAL in a single lecture. So whatever I have tried some very basic things. Then you can explore it further. So for reading, actually first we discuss about how the image is represented using JDAL. I like image raster data model of the JDAL. Actually, because JDAL can read a lot of raster data format, like you can say that almost all raster data formats. So the internal details of the all raster data formats will differ from each other. Like the way a GeoTIFF image is stored will be different from the way an IMG's image is stored. So because of this reason, so irrespective of the underlying format, the JDAL will represent and all images as a data set. So the data set in turn will have bands, and bands in turns will have the data arrays. So for opening an image, you need to first call the function called JDAL.open and pass it the name of the file which you want to read. So once you do this, it will return you a data set. From the data set, now suppose if you want to fetch some particular band, so in the data set dot get raster band and pass it the band number, which particular band you want to fetch. So once you get that band, so from that band you can call the function dot read as array and get the matrix or cell values of that particular pixel. And for visualizing the image, we have used the function called from the matplotlib plt.imshow. In matplotlib there is a pyplot module. So from the pyplot module we have called the function called imshow. So then we saw how do we calculate, how do we do some local analysis. Local analysis means the analysis will be done on the every pixel. So we saw how do we calculate NDVI for every pixel on our image, or NDWI for identifying the pixels, then how to mask the pixels, non-water pixels from our image. So with that, we come to the end of the lecture. If you have any questions, please post it on the chat box. I will try to answer to the best of my knowledge. So thank you very much. We will come back after 5 minutes.